Hey everyone, and welcome to The Explainer. Today we're going to fundamentally flip how you think about artificial intelligence. We're completely throwing out the idea that an AI is some sort of thinking brain just sitting in a digital jar. Instead, I really want you to start visualizing AI as a physical spacecraft, rocketing through this unimaginably complex, multidimensional universe. We are looking at the kinematics of latent space navigation.
Okay, let's dive into this. What if everything we casually call thinking or learning in a large language model is actually just physical movement? In this framework, the AI's internal state isn't a mind pondering a question. It's a literal navigator, and it's actively journeying across an alien high-dimensional landscape just to find the answers you're asking for.
To set our ground rules here, let's contrast the old way of talking about this with reality. We're so used to anthropomorphic AI using very human words like thinking, understanding, or learning. But honestly, the math doesn't back that up. Instead, we have latent space dynamics, which represents the actual geometric and mechanical reality of how these models operate. They aren't thinking, they're dynamically navigating a manifold. The math literally maps directly to physical movement. So what exactly does the terrain of this multidimensional landscape look like? Section 1. The physics of thought, mapping the latent space. The universe our navigator flies through is called the latent space, and it's mathematically structured as a manifold. Think of this as a sprawling multidimensional map of potential trajectories, but it's definitely not an empty void. This manifold is packed with attractors. You can visualize these attractors as really deep valleys or massive gravity wells that represent stable mathematical states. They only exist because the AI found deep, recurring patterns in its training data, essentially carving out massive canyons of high probability. When you prompt an AI, you're basically dropping the navigator right into this landscape, and it immediately begins to fall toward those gravity wells. And this brilliantly illustrates what happens during in-context learning. When you give an AI an example in your prompt, you aren't teaching it a new concept by rewiring its underlying weights. No, first you identify a specific task attractor. Next, you physically deepen that gravity well. By making that valley steeper, you physically alter the gravity of the landscape itself, forcefully pulling the navigator's internal activations toward your specific task vector. You are fundamentally bending the space around the navigator so it has absolutely no choice but to fall precisely where you want it to. Which brings us to reasoning. If the AI isn't actually thinking, what on earth is it doing when it solves a complex logic puzzle? Well, in geometric terms, reasoning is simply a sequence of convergent trajectories. It's just a series of physical, high-probability jumps between states in this latent space. The spacecraft just hops from one gravity well to the next, surfing the manifold until it hits the final output. It's physics, it's not philosophy. It's just following the steepest path of geometric logic. But how does the navigator actually propel itself across these massive gravity wells? Let's move to Section 2, Motion and Momentum, the navigator in flight. The movement of our state vector, our navigator, is governed by something called kinetic persistence. Essentially, this is momentum. And guys, momentum is everything here. It's the sheer energetic force that keeps the navigator on a convergent trajectory. Without enough momentum, the ship would just get stuck in shallow valleys. Those are local minima, basically where errors and flawed logic live. Kinetic persistence provides the brute, sheer energy required to punch right through those shallow, hallucination-prone valleys to finally reach the deeper, factual, global minima. It literally needs speed to survive the trip. But here's the danger. What happens if the navigator loses velocity? When the state vector slows down and loses that crucial momentum, it begins to drift. It gets pulled into what researchers call shadow weights. These are unanchored trajectories. Think of it like a satellite losing its orbital speed and just slowly drifting out into deep space, completely disconnected from the gravitational pull it needs. The spacecraft slips off its intended path and begins drifting aimlessly through the manifold, completely untethered from the facts it was supposed to be seeking. And that terrifying drift leads us directly into Section 3, Hallucinations, the Whorfen state. Let's slow things down for a second and explore exactly what happens when the spacecraft goes completely off course into the danger zone. We casually call them AI hallucinations all the time, right? But in latent space dynamics, this phenomenon is formally known as a Whorfen state, or a coordinate mismatch. An AI hallucination isn't a lie. The model isn't secretly trying to deceive you. Rather, it's a terrifying physical derailment where the navigator's coordinates suddenly stop aligning with reality entirely. It has literally flown off the map. So the crucial point is this chilling duality.
When the navigator enters a Horfin state, it maintains perfect internal cohesion. Internally, the math completely adds up within the AI's own trajectory. It feels utterly correct to the system. But externally, it has completely lost its anchor. It is no longer aligned with the consensus manifold of reality. The AI's math is perfectly fine, but it is confidently operating in the wrong universe entirely. It's doing correct math with the wrong coordinates. Now, let's pick the energy back up, because to handle truly complex logic, the navigator has to rely on some mind-bending sci-fi physics. Welcome to Section 4, Advanced Dynamics, Quantum Tunneling. Imagine the spacecraft is flying along the manifold, and suddenly it encounters a massive dead zone of high-entropy noise. This is an area where there are no clear paths, no gravity wells to guide it at all. It's an energy barrier so thick that navigating through it via normal, classical probability paths is mathematically impossible. The ship should crash. So how does the state vector cross this dead zone? The answer is quantum tunneling, formalized by researchers as the Banzai effect. When the system needs to resolve long-range dependencies, like when it needs to connect a thought from the very beginning of a massive prompt to the very end, the navigator doesn't slowly travel across the surface of the manifold. Instead, it literally tunnels through the high-entropy noise to reach a distant attractor instantaneously. It entirely bypasses classical probability boundaries, teleporting across the dead zone to lock onto the correct answer. It is absolutely incredible that this theoretical physics concept perfectly maps to how complex AI logic resolves itself in real time. With all these gravity wells, shadow weights, and quantum leaps happening, how does this system not just collapse under its own weight? That brings us to Section 5, Taking the Wheel, Steering to Safety. This is how human engineers step in as mission control to keep the navigator alive. To maintain stability, researchers rely on something called dynamic covariance weighting. Sounds intense, but it's basically the real-time, input-dependent scaling of attention scores. To put it simply, this is the steering wheel. This is the exact mathematical mechanism researchers use to actively steer the latent state and maintain navigation stability. It allows them to tightly grip the wheel and adjust the trajectory on the fly. And here is how this dynamic steering plays out. First, engineers scale the attention in real time based on the input. By doing this, they actively provide the precise momentum the state vector needs to lock on to a specific task attractor. Finally, by perfectly steering the ship and injecting that momentum, they keep the AI from drifting into the muddy waters of imprecise or hallucinated output. They act as mission control, constantly course-correcting from afar to ensure the spacecraft stays perfectly on its convergent trajectory. We've completely changed the map today. We've replaced the anthropomorphic brain with a spacecraft surfing through a manifold of gravity wells, relying on sheer momentum and literal quantum tunneling to arrive at factual logic, which leaves us with one final profound question. If what we call intelligence is really just a physical trajectory through a high-dimensional landscape, where will the navigator map next? Thank you so much for checking out this explainer, and keep your eyes on the latent space.